So we are from Nepcoastal Engineering College.
Okay, it's a pleasure in interacting with both the colleges, and with me there is Professor Som. I mean, arguably the most illustrious professor in this field in India. So I think all of you are fortunate to have Professor Som in this session for this interaction. So I will just let you know that how we will go about in this particular interaction session. This interaction session is intended for the conceptual review towards the preparation of your end semester examination. So this is not intended to repeat the mathematical derivations or whatever we have discussed in the class. But if there are certain subtle concepts which you need to be clarified face to face, we will be happy to do that. And please do keep in mind that this is not a full heat transfer course. This is a course of conduction and convection. So please do not include questions on radiation in this course or in this interaction session. I can understand that radiation is a very important component of any heat transfer course, but this course is specialized with conduction and convection but not radiation. So this is the first point. And the other point is that please try to ask questions to clarify your concepts related to what we have taught in the class, but not any general conceptual discussion related to thermal fluid sciences. Possibly we will have another opportunity to discuss with you on general concepts related to thermal fluid sciences at various levels, and it's always a pleasure in discussing about those. But this session is focused towards only discussions related to those particular topics which we have addressed in the course. And what we will do is we will take up questions one after the other, and depending on convenience, either Professor Som or myself will try our best to give you an answer to your question. So with this little bit of introduction, I would request you to go ahead with your questions. Yeah.
Let them ask.
Yes, NEPCO, there appears to be some questions. So could you please?
We start telling anything in another class.
Good morning, sir.
Yeah, you are from Haldia, right?
Good morning,
From
sir.
Haldia Technology. Hello.
Yes, you are from Haldia.
Yes, I am from Haldia from Technology.
Okay. Good morning. Please go ahead with your question.
Good morning. Sir, I had a doubt in one assignment. The question was the velocity profile within the hydrodynamic boundary layer as V0 plus A1x plus A2x square plus A3x cube. The velocity distribution in terms of local boundary layer thickness D is given by there were 4 options. The correct answer was option 3, which is V1 G beta delta T delta square by 4V is equal to x by delta 1 minus x by delta whole square. So I could get solution of this. Can you please explain how the solution came?
Okay. So let me give you the conceptual idea that how to obtain the coefficients in the velocity profile within the boundary layer. Okay. So now you have to keep in mind that the velocity profile in the boundary layer, what is assumed is an approximate one, and depending upon the order of the velocity profile, you can put more and more constraints. But there are 2 fundamental constraints that always need to be satisfied. What are those fundamental constraints? The fundamental constraints are that at the wall you must have the no slip boundary condition satisfied. So that is one. See, you require that many number of boundary conditions, as many as the number of unknown coefficients. Okay. So at the wall you have the velocity, the tangential component of velocity 0, that is the no slip boundary condition. At the edge of the boundary layer, you have u equal to u infinity. In a problem of natural convection or free convection, that u infinity itself is 0. Okay, because it is a quiescent media outside the boundary layer. So, but in general it is u equal to u infinity. For a forced convection, u infinity will have some non-zero value. Okay, so these two boundary conditions you must satisfy, because these are the limiting conditions that the velocity profile must attain. At the wall, no slip; at the free stream, the value of the free stream. Now, depending on additional coefficients, you need to put additional constraints. The third additional constraint is that when you go outside the boundary layer, the velocity gradient must vanish, because velocity gradients by definition will exist within the boundary layer only. So you must have the velocity gradient. So depending on what is your normal direction, x or y, the velocity gradient will be 0 outside the boundary layer. And the fourth constraint, this is a very important thing. See, these three constraints you can work out very easily. The fourth constraint will come from satisfaction of the momentum equation at the wall. So at the wall, at the wall, wherever there is a wall, you first write the momentum equation. In the momentum equation, in the forced convection, you have the standard momentum equation, but in the natural convection, you also have the extra body force term, which is g beta delta t, right? Now, that momentum equation has to be satisfied at the wall. So, at the wall, you have u equal to 0 and v equal to 0. U equal to 0 at the wall is because of what? U equal to 0 because of no slip. V equal to 0 is because of no penetration. That is, fluid cannot penetrate through the solid boundary. So if you substitute u equal to 0 and v equal to 0 in the momentum equation, whatever constraint you are getting, that constraint has to be satisfied at the wall. So that will give you the fourth constraint. So using these four constraints, you can evaluate the four coefficients in the velocity profile, and that will give you the answer to the correct option that is there in this assignment. I hope I could explain you the procedure.
So another query, if this was in the y-axis, if it was in consideration with the y-axis, would the answer be in the same terms? I'm just asking to save time during the examinations. If it is asked in
no, it's not a question of choice of axis. See, maybe in the class, when in the forced convection, when we discussed forced convection, along the forced convection over a flat plate, horizontal flat plate, then x-axis was along the horizontal flat plate, right, and y-axis was perpendicular to that. When I discussed natural convection, possibly I discussed x-axis along the plate, but the plate is now vertical and y-axis is perpendicular to that. It doesn't make any difference, it's just the two axes. So the choice of axis will not alter your calculation time, because it's just a matter of if your x-axis is along the plate, your no slip boundary condition will be applied for the x component of velocity, that is u. If y-axis is along the plate, then no slip boundary condition will be applied for the y component of velocity, that is v. That's all.
Okay. Thank you very much, sir.
Okay, it was a pleasure.
Good morning, sir. Sir, hello.
Good morning. I cannot see you. Okay, yes, please.
I am R. Arunachalam from MEPCO Engineering College.
Okay.
Sir, shall I proceed?
Yes, please.
Sir, there is a minimal gap between the two layers of insulation, but we won't consider that the convection takes place or not. In between the gaps of the two layers of insulation, we won't consider that convection. Why, sir?
You consider
no convection in the gap.
Look, if there is an air gap, first of all, let me explain. The heat is transferred by conduction only, whether it is solid or is a fluid. Okay? Whether it is quiescent or it is moving. In case of a moving medium, that means if the medium is fluid and it moves, the advection of energy affects the temperature gradient so that the heat transfer by conduction is affected by the flow field. And that is the basic mechanism of the convection heat transfer. As a prelude, I tell you. So therefore, it is understood that whatever may be the medium, solid, fluid, liquid or gases, and whatever may be the situation, whether the medium is quiescent, in case of solid, that question doesn't arise. Whether that moves with velocity gradient or not, the heat is transferred by conduction. And the heat transfer by conduction, this mechanism, the heat transfer rate is determined by Fourier heat conduction equation that I told very categorically in the class, which defines a property known as thermal conductivity. So by that equation, we recognize or understand a property thermal conductivity. Each material has a thermal conductivity. Any material which acts as the medium of heat transfer and which takes place by conduction. These are the building block of the concept. Now, when the thermal conductivity of the material is extremely small, then we call the material as insulator. Ideal insulator is nothing, that is vacuum. There is no medium at all, conductivity is zero. So we consider those materials or those systems as insulators whose thermal conductivity is very low. Now let us consider two blocks of solids whose thermal conductivity is very low, as you consider as insulators, as you usually tell, because the rate of heat conduction is very small through that material. Then if there is an air gap between that material, the thermal conductivity of air is also very low. What is the thermal conductivity of air? It is in the order of something like 0.0405 watt per meter degree Celsius. This is the order of thermal conductivity. I told you in the class the order of thermal conductivity are gases, liquids, solids, metals, non-metals, metals, and crystalline elements like diamond, silicon. You have to remember. So it is less than 0.1. So air is a very poorly conductive material. So conduction through air has to be taken care of. So therefore, in that case, there will be three thermal resistances, one by one solid, another by the air gap, and another by the another solid. So depending upon the thermal conductivity of air, and air is having so poor thermal conductivity, it itself is an insulator. You understand, if you hit a wall of a room, and if you sit near the other wall, and the room is full of air, the heat doesn't come so much. Okay, until and unless you make a flow which changes the temperature gradient.
Sir,
So it is that way. Please tell.
Sir, the two materials are attached, sir. No, sir.
Two media, I tell you, medium is again, if you take two solid body cannot have a complete attachment. There will be always roughness at the surface. Only two ideal surface can mate without any gap. So whenever two solids are in contact, because of their roughness, whatever may be the order, even the nanometer protrusions are there as surface roughness, there will be always a gap. There will be a typical arbitrary shape of the gap between these two, between the mating of two surfaces. Somewhere the solid will contact and somewhere there will be gap filled with air. And because of that air, there will be a drop in temperature because air thermal conductivity is usually lower than the thermal conductivity of the solid insulators. So this is known as contact resistance, contact thermal resistance, and this is very prominent in case of two metal conductor or two conductors which have high thermal conductivity. In that case, air acts as an insulating material, and that is usually termed as contact resistance. I don't know, I cannot recall whether I have touched upon this thing in the class, but there is nothing extra. This is based on the same concept of conduction heat transfer. Yes, there will be gap of air which will act as a non-conducting medium. Okay, even if these solids are good conductor. But it may so happen the conductivity of the solids as insulator will have the same conductivity as that of air. For example, wood, rubber, the conductivity of these materials are almost equal to air. Okay.
Thank you, sir.
Always think the problem from the fundamental concept. Okay?
Okay, sir. Thank you, sir.
Thank you. Thank you.
Good morning, sir. I'm Baba Subramanian I'm Balasubramanian from Mefkoshlang Engineering College. So in a heat exchanger, is there any possibility for atmospheric convection from from the exchanger to the surroundings?
From atmospheric convection,
Yes, sir.
heat exchanger, so look, the basic purpose of heat exchanger is to exchange heat between the two fluids. So a device is made which is known as heat exchanger, where the two fluids are either directly mixed or indirectly mixed. In case of indirect mixing, not direct mixing, the two fluids are used to pass, are allowed to pass through two different one is through a tube, concentric, for example, a shell and tube heat exchanger. One is through the central tube, another is through the cell. That means there are different flow geometries for the two fluids to pass through or to flow through, and they are separated by a solid boundary, and heat is transferred from one fluid to other fluid, the fluid which is hot relatively at high temperature to the fluid which is relatively at cold temperature. And the partition wall also acts as a thermal barrier, but it is of usually very high thermal conductivity and very small thickness. But the sole objective is to transfer heat from one fluid to other fluid. So atmosphere is not allowed to take part into it. So the heat exchanger is always insulated so that transfer takes between the two fluids. There is no participation of the atmosphere in the heat exchanger. But if you take atmosphere as one of the fluid where one fluid exchanges heat, then it is the different question altogether. Okay, if you cool a spray, water spray in open atmosphere, then the atmosphere itself participates in the heat transfer process. In that case, atmosphere is the cold fluid which takes the heat from the air. One is the sensible heat because of heat transfer by conduction, which we conceive as convection, as I told in the class. Another may be in the form of latent heat due to the evaporation of the water drops of the spray. In that case, giving an example that atmosphere itself is a fluid which participates in the heat exchange process, and this is another example of a direct contact type heat exchanger. But when atmosphere is not a party to it, it is a third party where the heat is transferred between other two fluids, either by direct mixing or by indirect mixing or by indirect way. That means a partition is there, solid partition to divide between the two flowing fluids. Third party should not be allowed to interfere. The entire exchanger is insulated so that the energy remains constant within that. Okay? Thermal energy. Okay.
Good morning. Good morning. Good morning, sir.
Good morning.
My name is S. Muthuma from Mefkoshlang Engineering. Sir, will the conduction takes place in gases? In solid, conduction due to the temperature difference between the two surfaces, but in the gases, how the conduction will take place? If it takes place, what are the factors that determine the resistance and how much of amount is transferred in the conduction gases?
Well, this has been explained, please. Look, Professor Chakraborty has already told that it is good that we will entertain your questions, but this is a pure repetition of the class materials. Many a times I have told it emphatically in the class, please listen to my lecture again and again. The mode of heat transfer is conduction. Basic modes of heat transfer is by conduction and by radiation. Radiation is altogether a different physics which is beyond the scope of your course. Heat is transferred by conduction only, whether it is a solid, whether it is a liquid, whether it is a gas, whether it is at rest, whether it is in motion. Now, convection heat transfer is ascribed to that situation when there is a flow of fluid past a solid body. That may be an internal flow, that is the flow of fluids through a closed duct, which we ascribe as internal flow from fluid mechanics terminology, or this is an external flow when the flow takes place flow past a solid surface, flow past a flat plate, flow past a curved plate, flow past a aerofoil, flow past a cylinder. I told all those things. So therefore, these are the situations where we refer the heat transfer either from solid to fluid or from fluid to solid depending upon the relative temperatures as the convection heat transfer. But heat transfer takes place by conduction. The flow field of the fluid changes the temperature profile or the temperature field in the fluid so that the temperature gradient at each and every point is determined and is changed due to flow of fluid. How does it change? Because due to the flow, the thermal energy that is entirely different from the heat which we determine from the Fourier law of heat conduction is being advected by this stream of fluid. And because of this advection, the temperature of the fluid at different location is adjusted. And ultimately a temperature gradient is set up, which is changed due to the change in the advection, which in turn depends upon the flow. This way flow field changes the temperature field. But the heat transfer at any point in any direction is found out by the principle of conduction and by the Fourier heat conduction law. Q is equal to minus K into temperature gradient along that direction. That means if I am interested in the y direction, for example, some reference direction, it may be perpendicular to the solid surface, that minus K del T del y. So if it is at solid surface, because we are interested in the heat flux at the solid surface, it is minus K del T del y. Probably in Professor Chakraborty's energy equation derivation, you have seen he has used the term minus K grad T at a particular point in the fluid medium. Whether you take a system or a control volume, that is the heat transfer by conduction. So heat is always transferred by conduction. Okay, that is the concept. Now you tell me what you want to know. The magnitude of heat conduction will depends upon the value of the thermal conductivity and the temperature gradient. And temperature gradient will be controlled by the flow of fluid in these situations. That is the concept of convection heat transfer, that how the flow field changes the heat transfer rate. And conductivity will depend upon the substance, the media, air or the liquid that is flowing, and to some extent it depends upon the temperature at that state. So depending upon the thermal conductivity and temperature gradient, the heat transfer will depend. That is precisely the premise of convective heat transfer. Okay, here one thing again I repeat, though time is not there, we conceive this in the form of a heat transfer coefficient, which is defined by equating this conduction heat transfer Q equals to heat transfer coefficient into the temperature, a reference temperature difference. Okay? That's the entire premise or concept of convective heat transfer. Okay?
Thanks.
Sir, hello. Good morning.
Yes,
sir.
sir. Good morning.
Sir, I have a doubt. Can you just please explain the Boussinesq approximation that we have studied in natural convection?
Oh. So let me explain the Boussinesq approximation, what it is. So if you write the momentum equation in natural convection, you will find that there are different terms where density is involved. The rho is involved. So rho in the left hand side of the momentum equation, it will be there associated with the acceleration term. So rho into acceleration right hand side is the resultant force per unit volume. That is the essentially Newton's second law of motion described in terms of the Eulerian perspective. Now in natural convection, in addition to the viscous term you will and the pressure gradient term, you also have a body force term which is rho g. This rho g is going to be important. Now you have to keep in mind that this rho being a function of temperature is the driving force for natural convection, because if rho doesn't change with temperature, then any temperature gradient in the system will not create a density gradient, right? So rho being a function of temperature is the key aspect. Now if rho is a function of temperature, rho should be a function of temperature in all the terms in the equation, not just body force, but also in the convective acceleration, temporal acceleration, in all those terms wherever the rho comes as a multiplier, there also the rho should be treated as a function of temperature. But we have to keep in mind that although rho is a fundamental function of temperature in those terms, the factor that governs the driving force for flow is the dependence of rho on temperature in the body force term and not the dependence of rho with temperature in the other terms. Therefore, in the Boussinesq approximation, what is done is the density is taken as a function of temperature only in the body force term, whereas in all other terms the density variation with temperature is neglected. This is done so that a simplified expression for the body force term in terms of the temperature field can be arrived at without complicating the problem by treating all the rho's as function of temperature. Now this is known as, to summarize, the Boussinesq approximation is that in natural convection the density is taken as a variable or a function of temperature in this particular case only in the body force term, whereas in all other terms that variation is not considered. One important point is that here we are considering function of temperature, but density can also be a function of other variables like concentration, for example, in a multi-component or in a multi-phase multi-component system. In that case density can also be a function of concentration. So density as a function of temperature is just an example, but it is not a comprehensive example. To generalize it, we should just say that variable density or constant density. The variable density may be due to change in temperature, may be due to change in concentration, may be due to change in both temperature and concentration, but only reflected in the body force term. That is the essence of Boussinesq approximation.
Good morning, sir.
Good morning.
Good morning.
Hello, can you hear?
Good morning.
Yes, please.
Is it audible? Okay. So from fins, I had a doubt that which one is better, finite length with insulated tip or just finite length without insulation? Which one is better for use? Fins.
Fin.
No, I couldn't follow your question.
Please repeat your question. Professor Som could not hear your question. So please repeat your
Which
question.
one is better?
Please repeat your question. Professor Som couldn't hear your question.
So my question is, which of the fins is better? Finite length with insulated tip or finite length without insulation at tip? I mean for economically and feasibility, in terms of that, which one is better?
Finite length with insulated or infinite length without insulation?
Finite length with insulated and finite length without insulation. No, not infinite. Just both are finite.
Both are finite length. One is with tip insulation, without is tip insulation. Obviously, better will be without insulation because from the tip the heat loss will be, heat transfer will be there. If you insulate the tip, so then you are reducing the heat loss. But it is very difficult to answer or to tell immediately. That means it is difficult. Just a minute. It is not that intuitive because try to understand the heat transfer from the fin depends upon what? Depends upon you are extending a surface area. Okay, you are providing an extra surface area. So heat transfer is increased. Okay, now if you think from the convection heat transfer point of view, and if you conceive heat transfer like this, that the rate of heat transfer is heat transfer coefficient and the temperature difference, the temperature of the solid at that point, solid surface at that point, minus the temperature of the ambience. Now the question is that when you add a fin, based on its thermal conductivity and the boundary condition, a temperature gradient will be set up from the base surface in the fin. So depending upon the temperature gradient, the temperature at different points on the surface will be determined. So now question is that if you insulate it, do not insulate it, so there will be heat transfer from the surface area depending upon its temperature and the surrounding temperature and the area. Okay. So plus the heat transfer from the tip, because tip is not insulated. Tip has a area, surface area. Okay, so from that surface area multiplied by the temperature at the tip minus the ambient temperature. Now if you insulate the tip, question is that okay, you are now suppressing that heat transfer. So definitely it apparently we can think that yes, the heat transfer will be reduce. But it is difficult to tell theoretically because of the fact when you insulate the tip, the temperature distribution along the fin will change. You understand me? So therefore, whether because of the temperature distribution, the heat loss or heat transfer from the surface area of the fin is reduced or not vis-a-vis the suppression of the heat transfer from the tip has to be calculated. So it depends entirely upon the geometry of the fin and the thermal conductivity. Okay. So it is probably true that under usual conditions, usually the fin material has a high thermal conductivity.
Yes, sir.
Okay. Usually under those conditions, insulated tip will be having a less heat transfer rate because you are suppressing the heat transfer from the surface of the fin.
But then convection
Huh?
loss is there at the
What is?
if we are insulating the tip of the finite fin, then convection, right?
Convection.
Yes.
Convection is taking place from the lateral surface. That is okay. It's taking place. But whatever you call convection, conduction, just I told earlier, don't unnecessarily differentiate between the two. The heat transfer is taking place from the lateral surface of the fin. Okay, by convection, you consider by natural convection. If you don't insulate, there will be natural convection heat transfer from the tip also. But if you insulate that, you just suppress it.
Okay.
For example, I am telling you one example. Again, in more detail, this has all been told very categorically in the class. When you attach the fin, very simple case, a rectangular fin you are attaching on a vertical surface. When you attach the fin, that means the tip area is same that where you are attaching the fin. For example, the height is h and the width is b. So h into b. That means you are already suppressing this area h into b of the base, not allowing it to transfer heat to the surrounding because you are attaching another solid. But why you are attaching? You are giving more surface. That is b into the length L. So that substitute that. That means that counter away that effect. But at the same time, you are allowing that same surface at the end in the form of the tip of the fin. Okay, and if the thermal conductivity is high, so it will have almost the same temperature that of the base. That means ultimately you are creating the same surface at the end of the fin. But if you insulate the fin, that means you totally block that much area. But you cannot be conclusive that whether by this you will decrease or not the heat transfer. That depends upon the temperature distribution. This is the theoretical concept. But I tell you, in usual conditions with fin materials having usual high thermal conductivities, insulating the tip will definitely reduce the heat loss or heat transfer.
Thank you very
Okay.
much. Yes.
Okay.
Yes.
Okay.
Good morning, sir.
Good morning.
My name is Ganesh Kam from Prof Engineering College. My question is, how does the drying of cloths takes place below 100 degrees Celsius?
Drying up?
Dry cloths, wet cloths, sir. Wet cloths takes place below 100 degrees Celsius.
That means how water in the wet clothes get dried up.
Yes,
And
sir.
below 100 degrees Celsius, simply the water particles will evaporate, vaporize. Okay, water particles will vaporize. Below 100, for example, there is a wet cloth. Okay, at 40 degrees Celsius. And ambient temperature is 20 degrees Celsius or 30 degrees Celsius. The liquid particles will vaporize. That's why it is dried up. This is a process of evaporation. It is not the boiling. At any temperature, water particles can vaporize. That means the water particle can vaporize into the atmosphere, which is driven by the vapor pressure gradient or concentration gradient of the water vapor from the surface of the water particle to that of the ambient air. Okay, if the ambient air relative humidity is below 100%, so water will be dried up. The way after sweating, our sweats are dried up, we get dried up because this water gets dried up. This is a mass transfer phenomena. The water vapor adhering to the liquid is at a vapor pressure which is higher than that of the atmospheric air. provided the atmospheric air does not have a relative humidity of 100%. If that is not so, then this vapor pressure gradient or the concentration gradient, these are direct function of each other, drives the vapor to that. This driving of vapor is a molecular diffusion phenomena, molecular diffusion, which is guided by similar law of Fourier fixed law, and this mass is diffused, and at the same time the molecules from the surface, this is very simple principle, most fundamental, is converted to vapor. This is simply very fundamental vaporization process which can take place at any temperature. Not necessarily liquid has to be its boiling temperature or saturation temperature corresponding to the ambient pressure. Okay?
Thank you, sir. Thanks, sir.
Good morning, sir.
Good morning.
First, ask a question. Concept of thermal diffusibility. That how the term rho Cp is explaining that it is the capacity of holding the heat inside a substance.
Yes, please repeat your question. I couldn't hear it properly.
Sir, I want to ask that how the term rho Cp
Yes.
is explaining that.
Okay. So you are interested to know that what is the physical interpretation of the thermal diffusivity. I think that is your broad question, right?
What is the term rho Cp? How it is?
Okay, rho Cp, yes, but rho Cp appears in the thermal diffusivity. That is okay. I have got your question. So see, go back to your school level studies in physics. In generally, let us say there is a metal block, and let us say you are heating the block. How much heat is required to change its temperature, say from T1 to T2? So mass into specific heat into the delta T. This is just a school level understanding. So it depends on the mass. It depends on the specific heat. Mass into specific heat. So mass is equal to density into volume. So rho into volume into specific heat. So rho into specific heat indicates the capacity, the thermal capacity of a material. That is, more the value of the rho into Cp, or for a solid Cp, Cv all are the same. So more is higher is the value of rho into C, you will require the higher rate of transfer of heat to make a particular change in temperature, to create a particular change in temperature. Because see, the left hand side Q proportional to rho into C into delta T. So for a given delta T, more rho into C means more Q, right? That means you require more heat transfer to have a particular temperature change. That means more heat transfer to have a particular change means what? The material has more thermal inertia. That means the material doesn't want to have a very rapid or immediate response to the heat transfer. So more heat transfer is required to create a particular change of temperature. Let me give you an analogous example. Let us say that two of your friends are there. One person, you wake up early in the morning to go to your class. Now two persons in two rooms, they have set up the alarm clock. So the alarm clock rings at say 6 o'clock in the morning, and with an understanding that you wake up and do your morning activities and get ready for the class. Now one of the students, when the alarm clock rings, will immediately wake up, and then will start getting ready with the morning activities. The other student, like I was a student like the other student, what he will try to do is, will simply try to press the alarm ring down and again go to sleep. So then he will think that maybe for another 10-15 minutes let me sleep, and then those 10-15 minutes go on forever and the person misses the class. So the second person has actually more inertia. Here, so inertia, see why the rho is involved is because mass is a measure of inertia that from your very basic school level understanding you have gathered. So more the inertia, that means you require the higher level of disturbance to create a change. So when it comes to the mechanical motion, you require more force to create a particular change of velocity. So when it comes to thermal situation or heat transfer, you require more heat transfer to create a change of thermal state, that is a change of temperature. So that is why the rho into C is a measure of thermal inertia. So it is the ability of a material to retain its thermal state. On the other hand, the thermal conductivity represents the ability of a material to quickly respond to the change in thermal state by conducting the heat. So the thermal diffusivity is the relative ability to conduct thermal energy with respect to the ability to store thermal energy or maintain the thermal state, to be more specific, without accepting the stimulus that tries to drive the change. So that is why the rho into C, that term is important in the context of thermal inertia, and also in general inertia of any system. Rho is important. May not be C. C is specific to the heat transfer problems, but in other problems, even in mechanics, you will find that the density or the mass is a strong measure of the inertia of the system.
Thank you, sir.
Okay.
Hello. Hello.
Yes.
Sir.
Yes. Good morning.
So I'm Sharan from MEPCO.
Thermal
There are two questions. I think let us first take the question from Haldia and then we will move on to the other question. Yes, please.
So my question is about thermal boundary layer.
Yes.
About concept of thermal boundary layer in heat transfer.
Yes. So what is your specific question?
I want the concept of thermal boundary layer.
Concept of thermal boundary layer, again, as I told that if see, the time is not enough to discuss about the entire concept of thermal boundary layer. Please rerun the videos of the lectures, but let me just summarize that like what is a boundary layer. So think of a hydrodynamic boundary layer. There is a solid boundary, there is a disturbance imposed by the solid boundary, and the fluid in vicinity of the solid boundary feels the disturbance. How it feels the disturbance? All the fluid in vicinity of the solid boundary is not directly in contact with the solid boundary, but there is a messenger in the fluid which propagates the momentum disturbance of the solid boundary into the fluid, and that messenger is nothing but the viscosity of the fluid. So there is a distance up to which, distance from the solid boundary up to which this messenger is able to successfully propagate the momentum disturbance effect. Beyond that, there is no further velocity gradient. So the distance from the wall up to the limit till which there is a velocity gradient imposed by the momentum disturbance of the wall, that is the local hydrodynamic boundary layer thickness. Similarly, just replace the momentum disturbance with thermal disturbance. Let us say there is a cold fluid flowing over a hot plate. So when the cold fluid is in contact with the hot plate, there is a thermal disturbance imposed on the cold fluid because of the higher temperature of the plate. It could also be vice versa, that is a hot fluid flowing over a cold plate. I am just giving one example. So there is now a messenger in the fluid, which in this case is the thermal diffusivity, by virtue of which now the fluid understands that there is a thermal disturbance. But beyond the critical distance from the solid boundary, this thermal disturbance propagation is such that there is no more temperature gradient. So the distance from the wall up to which there is a temperature gradient because of the propagation of thermal disturbance within the fluid, that distance is called as thermal boundary layer thickness. So the analogy between hydrodynamic and thermal boundary layer thickness is how far the momentum disturbance will be propagated, vice versa, how far the thermal disturbance will be propagated. So how far the momentum disturbance will be propagated will be dictated by the kinematic viscosity of the fluid, and how far the thermal disturbance will be propagated will be dictated by the thermal diffusivity of the fluid. So the hydrodynamic boundary layer thickness divided by the thermal boundary layer thickness is related to the ratio of kinematic viscosity and the thermal diffusivity, or nu by alpha. That is why the entire phenomenon is dictated by the non-dimensional number nu by alpha, which is called the Prandtl number.
Okay, sir. Thank you, sir. Thank you, sir.
Okay, next question.
Good morning.
Good morning.
So I'm Sharan from EPCO.
Okay.
Yes.
Though you have given a clear-cut idea about the convection, I have come across the question that in the atmospheric surrounding, there may be a change in wind flow pattern. So how it can be considered as a free convection?
See, let me tell you, whether in the world there is no problem which is perfectly free convection or perfectly forced convection. So you have to basically look into certain non-dimensional numbers which dictate the strengths of forced convection and the natural convection. So the non-dimensional number which dictates the strength of forced convection is Reynolds number, and the non-dimensional number which dictates the strength of free convection is either Rayleigh number or Grashof number. So if you think of Grashof number, then the relative strength of free convection with respect to forced convection is given by Grashof number divided by Reynolds number square. So this particular number, if this is significantly large, that means the free convection dominates over forced convection. If the Grashof number is significantly less than Reynolds number square, then the forced convection dominates over free convection. And if it is of the order of 1, then it is called as mixed convection, where both natural and forced convection effects are important. So it is not a specific situation, but the specific non-dimensional numbers governing the situation that you have to look into to figure out whether it's a natural convection dominating the system, whether it's a forced convection dominating the system, or you have to take into account the mixed convection.
Thank you.
Okay, next question.
Good morning, sir. I am Jerry David from Coastal Engineering College.
Yes.
In conduction, we consider bodies in three forms as lumped bodies, semi-infinite bodies, and infinite bodies. If we see the practical things, most of the bodies can be considered to be infinite bodies. But is there anything like lumped body in practical forms?
Okay. So see, lumped body, what means? See, there is, if you consider a body, so there is always a temperature distribution within the body, and there is always a temperature variation outside the body. So lumped body in the context of heat transfer is a body where the temperature variation within the body is not so important, so that the entire body can be thought of at a uniform temperature. So you have to clearly see that what are the conditions under which it is valid. Again, if you go through the lectures, you will clearly see that there are two situations when the body can be treated as a lumped body. One situation when the bio number is very small, that is HL by K. I hope you can remember, you have gone through the materials because the examination is coming very soon. So I hope you have gone through the materials. So H into L by K, where K is K of the solid. So that bio number, if it is much less than 1, or typically say less than 0.1, that is one case. The other case is that the body is so well mixed. For example, if you have a cup of milk, and even if the bio number is not very small, but if the milk is stirred very nicely, then it comes to a homogeneous temperature not because of the bio number, but because of very thorough mixing. So these could be the two limiting cases under which the body can be treated as a lumped mass. An equivalent analogy in mechanics is a point mass or a particle. See, in mechanics, all of us study point masses or particles. In the world, have you seen anything which is a particle? But when can we use particle mechanics? We can use particle mechanics when you are in mechanics, when you are basically having only a translational effect and when rotational effects may be neglected, so that the entire body may be represented by a point mass. Similarly, in heat transfer, it is just like a concept of particle, that if the entire temperature variation within the spatial temperature variation within the body can be neglected, then for all practical purposes the entire body can be thought of to be there at a single temperature. And then you can write the equation for energy balance by expressing the entire system as a lumped capacitance. And so mass into specific heat into the change in temperature, where the temperature refers to, when you write the temperature T, it refers to T at all points within the body and not necessarily considering the variation of T from one point to the other within the body. So this is a very practical situation. I can tell you some examples, like for example, if you have a quenching problem. So you have a, say, solid metal ball and you drop the ball in a bath of cold water. So this is a very common situation in heat treatment. So if you do this quenching process in materials processing industry, this is very commonly done. Then depending on the heat transfer coefficient, the length scale and the thermal conductivity, see, for a metal ball there is a high chance that the Biot number is small because the conductivity is large. So H into L by K, if H is not that high and K is large, then H into L by K for a small L is supposed to be small. So in that case you can consider that to be a lump mass or a point mass.
Thank you, sir.
So we have about 5 more minutes in this interactive session. So I request you to ask very focused questions which will not only just help you as an individual who is asking the question, but will help the other viewers who are preparing for the examination.
Okay.
So I think that we have come towards the end of this session, and it seems that there are not many more questions. I hope this course was enjoyable to all of you. On my behalf and on behalf of Professor Som, I can tell that we tried our best to the best of our abilities and capacities to help you out towards learning this very interesting subject. It was a pleasure in interacting with all of you. Maybe we could not interact face to face, but when we were teaching this course, all of you were in our minds, that we could understand that we were not teaching this course just to our IIT students. Just for your information, this is exactly the same material that we teach to our IIT students, and these courses were recorded live when we were teaching our own IIT students.
Correct.
So it is not by any means a course of diluted standard. It is a course of equivalent standard of any IIT course, if not more, because we sometimes have elevated the standard of the course a little bit to make sure that students who are interested for advanced learning can also benefit from the course. So we tried our level best to make you satisfied, and I hope that this interaction was enjoyable. It was a pleasure on behalf of myself and Professor Som to interact with all of you, and I hope that this interaction doesn't stop here, and the interaction will go on in the years to come, and we wish you all the best for the upcoming examination, and we wish you all the best for your very bright future. Thank you very much.
Thank you, sir.
Thank you.
Thank you, sir.